In this lesson, we're going to define general prisms and cylinders, and then in class we'll talk about cross sections. So we'll start right off with the definition or some properties of a general cylinder. So the first property of a general cylinder is the fact that it has parallel, congruent bases. It doesn't really matter what the bases look like, but they have to be parallel to each other, and they've got to be the same size and shape. So here is a kind of a strange diagram, but it represents what a general cylinder looks like. Again, it doesn't look like a can, it doesn't have to, as long as your bases are parallel and congruent. So as I just stated, the bases of a cylinder, they don't have to be circles. They can be curved, or they could also be polygons, and they would still meet the qualification of being a cylinder, which is parallel, congruent bases. And then one more thing for the general cylinder is that the sides do not have to be perpendicular to the bases. And again, that's what's demonstrated in this image here. As long as the bases are congruent and parallel, the sides will connect one to the other, but they don't have to be at right angle. Those are more specific types of cylinder. These are just the qualities of a general cylinder. So within that family of cylinders, we have something called a prism. So a prism is a general cylinder where the bases are congruent polygons. So you don't have curves. The edges are line segments. And then within the definition of prism, we have something called a right prism. So a right prism is a prism where the sides are perpendicular to the bases. Think of a box. And it doesn't just have to be a box. It can be any polygon. So I don't know if I can draw one, but it can even be, let's say, a hexagon. If that, well, that's terrible drawing. If that's one of my bases, and then if all of these edges are at right angles, this is going to be a right prism. And then finally, the last one is an oblique prism. And that's where the sides are not perpendicular to the bases. So the bases are still parallel to each other, but the sides don't have to be at right angles. I don't know if I can draw one very well. If I try to draw my hexagon again, it's kind of tough to do this in 2 dimensions, but it would be where the sides are at an angle. Yeah, that's a terrible job. I will show you more examples in class, but just remember that this is a right prism where the sides are straight up and down compared to the flat bottom and the flat top. The horizontal bottom, horizontal top. Here, that's terrible drawing, but it's at an angle even though the bases are still parallel. If you look at the original diagram, if the original one at the top of your paper were just all polygon sides, then it would be an oblique prism. I'll try to draw one like that. I still can't do it. Yeah, we'll look at those in class. So when I'm dealing with a prism, we also have lateral faces and lateral edges. So here's a picture of a right prism here. And the faces are one side of a prism. So in this case, the parallel sides are the bases are the top and the bottom, and the faces are going to be these sides here that are vertical. So a face is one side of a prism, and then we have lateral edges. The lateral edges connect the faces. So you can see the lateral edges are these vertical lines. So a lateral edge will connect the 2 lateral faces. For example, P2 and P2 prime. This is a lateral edge. P2, P2 prime. And then we talk about the lateral area. So the lateral area is going to be the area of all the lateral faces. So it's the surface area of the prism minus the bases, the base area. So if you wanted to determine the lateral area, you could calculate the area of all the faces and then add them up. Or if you were to split this guy and lay him out flat, he's really going to be the perimeter of a base multiplied by the height. Because anytime you split this and lay it out, you're going to get a big old rectangle. So that's another way of calculating the area of the lateral faces. So again, it can be calculated by finding the perimeter of the base and then multiplying that by the prism height. So those are prisms, and now we have a right cylinder. A right cylinder you might think of as like a Coke can, but it's more than that. Any bases that contain curves. So this thing here is considered a right cylinder because the bases are curved and the sides are perpendicular to the bases. So anything that's not a polygon is going to be considered a cylinder, and a cylinder whose sides are perpendicular is going to be a right cylinder. So a right cylinder has sides perpendicular to the bases, which means an oblique cylinder would have the sides that are not perpendicular to the bases. And then we have a circular cylinder. This is what most kids, most students think of as a cylinder right here. The bases are congruent circles. So in this case, what you see here, this is a right circular cylinder. We could also have an oblique circular cylinder, but a circular cylinder, this is to get you to understand that it's just one part of the whole family of different cylinders that we could have. And in every case, if we want to find the volume of a right general cylinder, and it really doesn't even have to be a right general cylinder. If you want to find the volume of a cylinder, it's going to be the product of the base area and the vertical height. So this works for any cylinder. It's going to be the product of the base area B and the vertical height H. So the general formula for volume is going to be capital B times H. You have to remember that capital B stands for base area. It is not a linear dimension. It is an area dimension because volume is a cubic dimension. So this dimension is squared, the height is linear, and that's how you get the volume. So here's an example of how we use that. A right cylinder has a base area of 50 square inches and a height of 7 inches. Find the volume. This is about one of the easiest problems you're going to get. Base area is capital B. That's 50 square inches. The height is 7 inches. Both of our units match, so I'm good. That's the first thing you got to check. And then the volume is just going to be the product of the two. So 50 times 7. So in this case, it's going to be 350 cubic inches. It's as simple as that. So quite often you'll be given the base area, and all you have to do is multiply by the height to get the volume. In the second example, a right cylinder has a volume of 200 cubic feet and a base area of 25 square feet. We can work backwards and find the height of the cylinder because we know the volume is the base area times the height. In this case, I'm given the volume, I'm given the base area, and I'm trying to find the height. So you divide each by 25, and the height is going to be 8 feet. Everything's in feet, and I should have checked that in the beginning. This is cubic feet, this is square feet, so our height is going to be 8 feet. The next discussion entails identifying a cross-section versus a slice, and we're going to actually talk about that in class. And then I want to show you an example in class from the latest Regents exam where they did not follow this definition. So that's kind of a problem, but we're going to define it anyway the way the curriculum tells us to, and we're going to talk about that in class. But to finish off these notes, we're going to look at what happens when I spin a rectangle around an axis. So if we were to rotate this rectangle about this axis, like spin it around, it's going to sweep out a cylinder. And that's true whether this image is a square or a rectangle, any kind of rectangular region. Anytime a rectangular region is rotating around an axis, a cylinder is going to be created. And the width of the rectangle is the radius of the cylinder. So here's the radius, here's the radius, here's the height, here's the height. And that's just something you have to think about in your head when you spin something around. What kind of image does it sweep out? And we're going to do other things we're going to look at other images as well and see what kind of shapes they form when we spin them. So again, in class we're going to talk about cross sections and slices, and we're going to work on all these volume definitions and calculations.